So Ben is joining us tonight to talk about a subject near and dear to my heart. He's going to talk about dynamic analysis for software security. Thanks, Ben. And like before, if you have questions, put them in the chat. And Ben, would you like them to hold questions to the end, or do you want?
Oh, you guys can ask whenever. I might be moving kind of fast because I got a little carried away, but I'm happy to stop and talk. The slides are all online in my URL there, benholland.com. So if you want to dig into them or look ahead, go for it. But yeah, great. I'm just definitely something I'm pretty excited about. So
great. Thanks, Ben. We'll let you take it away.
Yep. And we can see I'm sharing the slides, right? Is that?
Yes.
Okay, great.
Yep.
Okay. Yeah. So this is about dynamic analysis. So a little about me. I was a kind of forever student for a long time, finally graduated in 2018, moved out here to DC metro area. I'm currently working at a company called Apogee Research, where currently we're 100% funded by DARPA research. So if you kind of like the things that I'm talking about, we are hiring. Just a small plug there, but definitely check us out. So a little disclaimer, I'm not here on behalf of my company. I'll probably even get some things wrong, and I try to be unbiased if I can, but I'm definitely going to be biased towards some approaches. I mean, part of these things were kind of pulled from my PhD. So what I wanted to talk about today, real brief outline, was what is a program? Why do we need program analysis? What is dynamic analysis specifically? And then let's take a look at what's the state of the art in dynamic analysis. And let's go like as far as we can with it. And then kind of question, how can we do better? And I have an opinion, but I don't have an answer specifically. So first of all, what is a program, right? And when I taught a class at Iowa State, I used to ask this as kind of an icebreaker exercise, right? My mom would always ask me every year, what am I doing in school? And, what is this computer programming thing? And I would try to explain it, and I never quite get it right. And eventually she stopped asking. So I either got it right, and I know what it is that I said when she stopped asking, or she never got the answer she wanted. She stopped asking, right? But could you come up with an explanation that intuitively explains, what is a program? What are these input outputs to programs? Where's all this complexity of software come from? What are programming bugs? Where do we get these security issues from, right? And I always gave the same answer, and it's funny because my students always give the same answer too. And it was just, well, it's a set of instructions, right? And you kind of elaborate on that, and you kind of go deeper. Eventually, I kind of started refining that answer a little bit. I said, well, it's similar to a cooking recipe, right? We have an ordered list of instructions, some sequence we can follow, and specifically, we could visualize that sequence of instructions, and we could visualize it as a flowchart. So I'll come back to that idea. But these instructions are executable, right? The cook knows how to execute these, or the computer knows how to execute the instructions. Instructions have operators, operands, right? So basically the operation you're going to do and the data that you need for that operation. So for example, a cooking recipe instruction might be that I'm going to add, and then the operands are flour and bowl. So I'm going to add flour to a bowl. And we can actually have branching and non-branching instructions. And this is where things start to get, the complexity starts to creep in. So we can say, if you're baking a large batch, then add an extra flour to the bowl, right? Do that instruction again. And then we can repeat instructions, right? So we can jump back to the first instruction, repeat, or we can do things like, while the batter's running, keep stirring the batter, right? And we could refine this a little bit more. You can kind of keep going in this direction, right? So you could even say, well, maybe an even better answer is something that could be translated to a low-level set of instructions. Example, I'm going to say brain fudges last time because I said it out loud and I got censored last time. So a brain fudge program that controls a Turing machine, right? So brain fudge is basically just a very simple set of instructions that controls this kind of theoretical model of a computer, which is a Turing machine. We have this infinite tape that extends. In fact, you don't even need infinite to be Turing complete. You need like 30,000 cells or something like that. And we can read and write a symbol to that tape. So in this case, brain fudge does it by letting you increment and decrement an integer. The symbol is just an integer. And we can move our pointer of the one cell that we're allowed to interact with at a time by moving the tape, the pointer on the tape left, or moving the pointer on the tape right. We can also do some branching and looping. So we can say, if the current cell that I'm looking at is not 0, then jump to this other command. Or if it is 0, repeat until if it's not 0, repeat until it is 0, right? So very simple instructions. This is Turing complete. And pretty simple to map this to a Turing machine. But what are the inputs and outputs? Well, in a Turing machine, the inputs are just the data that you had on the tape when you started executing the program. And the output is the data that's on the tape when you finished executing the program. And you can kind of go pretty far with this. And I have built some simulators and things to play with this if anyone wants to look at that stuff later. But, so it's pretty simple. We can all understand that very simple little model. So we have a little brain fudge program. And, we could build on this if we wanted to. We could say, well, we could write a C compiler that compiles a C program down to brain fudge, and people have done that. And I found a really nice article that kind of walks you through the step, like how to set up the stack, how to make functions, things like that. And, from there, we could build things even more. We could build a JavaScript interpreter. We could build Java, Python interpreter, all sorts of things. We can kind of build out from this. And, obviously, we have much more efficient architectures that run on things. We could do things like add and multiply directly on a CPU. Now we don't have to do just increment and decrement by one, but this kind of gives you a foundation for, okay, if the program is this simple, where does all this complexity and security bugs and stuff break into it? It's only 6 instructions, right? How could I mess this up? Well, this kind of leads us to the next question. So how do we get, why do we need program analysis? Well, I want to make some statements and I'll try to back them up. So I want to say that programs have a staggering amount of complexity. And we have a lot of programs. Programs are changing at a ridiculous pace. They're infested with bugs that can last years. And we still haven't learned how to write correct software. So let's kind of go through each one of those one by one. So if we think about the complexity in software. Remember we said we could visualize software as a flowchart, right? I want to make the hypothesis. In fact, I had this hypothesis, and spoiler is that this is actually true. So I at one point said, I believe there are more paths in the Linux kernel than there are atoms in the known universe, right? And I went searching. I wanted to prove this. So first, you can just Google this, but how many atoms are in the known universe, right? So you say, okay, well, the known universe that we know of is 93 billion light years. There's roughly 500 billion galaxies, each with approximately 400 billion stars. So, we're starting to get to big numbers already, but then we can say, okay, well, how many grams are in a star? We have some average and look at gravity, things like that. Well, we can say each gram of matter is 10 to 24 protons, and hydrogen atom only has 1 proton. So that gives us kind of a high bound estimate on the number of atoms in the known universe. That's 10 to the 86. And so out loud, that's 1,000 quadrillion vigintillion, however you say that, right? So when it sounds like a first grader is just making up numbers, and it's a big number. And all right, so let's look at the other side. So how many paths are there in the Linux kernel? So how do you count paths? Well, if you have a branch, that gives you 2 options, right? And if you have these independent branches, non-nested, well, now we get an exponential number of paths, because if you have 1 branch, you have 2 paths. If you have 2 non-nested branches, you have 4 paths. If you have 3, you have 8, right? So it's to the n, and it grows exponentially. So, okay, I figured, I'll go looking for some code in the Linux kernel that has these properties. And in fact, I didn't have to look very far, and I didn't even have to look outside of one single function in the Linux kernel. So I found one function in the Linux kernel that had 2 to the 656 of these repeating patterns. Remember, there's only 10 to the 86 atoms in the known universe. 2 to the 656 is 10 to the 197. So substantially more paths. And, if I were to start looking at how functions call other functions, well, that's multiplicative, right? So it just grows. And then once we start adding loops, we're just testing the limits of human comprehension. So the path explosion problem is a problem that you hear people in program analysis talk about all the time. So the complexity is there, and it grows substantially, very, very fast. And to make things worse, we have a lot of programs. We're not just talking about one function in Linux kernel. We're not talking about Linux kernel. We're talking about lots and lots of programs. And I tried to find, I was like, how many programs are there in Google, right? And we just don't know. I can find 700 fully featured programming languages. GitHub had 100 million open source repos as of 2018. And I found an estimate that we write 111 billion new lines of code a year, but yeah, that's just napkin math. We have no idea. There's enough programs that GitHub plans to archive the source code at the North Pole, which I thought was kind of fun. So it's right down the street from the seed vault. There's a abandoned mine where they're going to archive all these programs on kind of microfilm. And so, you can imagine if you had, I believe you had 1 star on your GitHub repo, it would get included in this archive. So all of those bugs in your programs are going to get buried in the permafrost for the next 1,000 years, which is kind of fun to think about. And programs are just changing at this ridiculous pace. We don't just have one program, we have a snapshot of programs, right? If we just look at the Linux kernel, we're adding 2,000, over 2,000 lines of code a day. We have 795 lines of code added an hour. That's almost 20,000 lines a day. We have just as many that we're removing. Actually, I think that's a typo. That's the same number. I typoed that one. But code contributions in 2017, this is spread out over 15,000 developers and 500 companies, right? So think, and software is infested with bugs. I think we all know this because we're in this field, but these bugs can last years. So I found a statistic, industry average is 10 to 50 defects per 1,000 lines of code. That doesn't necessarily translate to exploitable bugs or vulnerabilities, but just issues per 1,000 lines of code, right? And we know that these vulnerabilities can live for a long time. So on average, they're in the code base for over a year before they're even discovered. Shell shock was around for 25 years after it was created, after the bug was there. We find 0 days go undetected for almost a year before they're discovered. And to get the security patch to come from the other side, well, it takes almost a month to, so the security patch is created about a month before the vulnerability is disclosed publicly in the situations where that happens. But we see organizations taking 100 to 120 days on average to patch the vulnerability. And the highest remediation time was actually in the financial industry. So exploits have appeared pretty quickly, sometimes as short as 3 days after the disclosure. And the average life expectancy that these exploits are maintained and kind of modified, mutated is almost 7 years. The probability that a vulnerability will be exploited in those first 40 to 60 days, well under the remediation time, is near 90%. So, if you're going to get it, it's going to happen early. But we keep making the same mistakes, right? So if you look at the Linux kernel and you look at the patches in the Linux kernel, 15 to 25% of the patches for bugs were themselves buggy, right? So they required follow-up patches to actually get it right. And if you look at Android, 85% of the high severity vulnerabilities were all because of like low-level data structure issues, right? Which makes sense because that's where you can gain a lot of control of the device. But these low-level issues are things like buffer overflows, right? In fact, if we look at things like buffer bound issues specifically, almost 1 in 4 of all of the high and critical severity CVEs between 2000 and 2019, which is all the CVEs I could get my hands on, were related to buffer bound issues. So 1 in 4, right? For things like buffer overflows, which were first documented in 1972, smashing stacks 1996, right? We just can't get this stuff right. And there's a reason for it. It has to do with the complexity, but there's a lot. This is a very challenging problem, right? So, okay, one of the solutions we've pitched, what is dynamic analysis? So broadly speaking, there's kind of 2 ways you can approach analyzing programs. So static analysis, don't run the program. We're going to dissect it, look at the logic, examine the artifacts in the program, kind of get this bird's eye view of everything that could possibly happen during the execution. But, as we just talked about that path explosion problem, there's a huge number of behaviors in this program. And we don't know if all of them are actually feasible. Just because you find a path in the program that looks bad doesn't mean you could actually execute that path at runtime. There may be constraints that prevent that path from ever being executed. Well, there's the other side of it. We could run the program and we could feed some inputs in and see what it does, right? So we don't have this problem of like what's possible. Everything that we see the program do is possible because we just saw it happen, right? Now, we have a similar problem. If we think about the number of inputs, well, it's binary, it's to the n as well, and that's with the length of the input, and we have huge input streams. So the input space is also huge. The question is, did I feed it the right inputs to test the interesting things in the program that I actually care about, right? So you kind of have this opposite problem of, where static analysis, we don't necessarily know if the thing I'm looking at is actually a problem, whereas in dynamic analysis is, did I actually test all the things that I care about, right? And they have the same kind of problem, but from 2 different ends. And then there's always the problem of what am I looking for, right? So just because we're, not all programs translate to a crash, right? So we might have to come up with a way to translate to a crash. If it's things like business logic errors, it might be a bad calculation, or it might be like authentication logic, something like that doesn't necessarily crash the program. So we also have to have some idea of what we're looking for. And I gave a previous talk at SecDSM that kind of hit on that question a bit more, and also the static analysis side of things, which is the camp I originally came from. So before I go on, I want to say that, a lot of people kind of stop there. So there's static analysis, there's dynamic analysis, but actually there's a huge spectrum of analysis techniques. And they range anywhere from, really static to really dynamic to something in between. So like symbolic execution is running the code symbolically, right? It's kind of a little bit of both. And we can also add another spectrum, which is it a manual? Is there human involvement, or is it fully automatic, right? We could plot things here, and I've shown this slide before. That I actually stole this slide from Julian Conan in Black Hat 2014 talk, really good talk. But you can argue where things are on in the spectrum, right? And people will disagree with that. But the point is really there's this kind of blend of different approaches. So let's kind of do deep dive into dynamic analysis. And I want to break it down into some key questions. At least these are what I think the key questions are for dynamic analysis. So you can take any dynamic analysis technique and you can ask these questions and try to understand it that way. So the first question is, what is monitored in the program? Then how do we generate inputs? What are we searching for? And what is executed in the program? So let's start with the first question. What's executed in the program? What's monitored in the program? And there's kind of, this is where these terms black box, gray box, white box come in. So black box is, I don't know anything about the program. It's just a black box. I feed inputs in, I get outputs out. And that's all I can really do. Gray box says, okay, I'm allowed to look at some things. I can kind of peek inside the box. Whereas white box is, okay, I can have everything. You could imagine you have source code, but really you don't have to, I wouldn't say that having source code is a requirement for white box testing. Having access to all of the binary code you can do some of the same techniques on binary code directly. So start with black box and we'll kind of work our way up. So black box, how are the inputs generated? Well, so if it's just a black box, it's just a program. I'm not allowed to look inside. I'm not allowed to know anything really about it except from what I feed in and what I get out. Well, I can generate some set of test cases, right? I might have something like a bunch of test cases that I know are interesting. If it's a web server, I might just shove a bunch of, strings that I know might happen to be cross-site scripting attacks, or, generate things that if it comes out in the output, it's tainted the output. Like, I'm looking for reflection, what's it called? Reflected cross-site scripting, something like that. I'm not really allowed to look at much else, right? If I'm looking for a crash, most of these fuzzers are looking for a crash, or they're looking for some specific thing, right? You can't just fuzz without knowing what you're looking for. You want to know when to stop. But we can generate some test inputs, or we could just start with a list of known test inputs, right? And then we might randomly mutate that list to generate new ones. But that's really all we can do with black box testing. I'd be curious to know if someone thinks something else. But until you start saying I'm allowed to look at more, then we can start to do things that are more interesting. So again, what's the input space? Well, it's exponentials to the n. If it's a looping, it's reading like a stream. Well, it could be potentially infinite, right? It could just be processing data in a loop. So we have to come up with some interesting way to generate the inputs. And at this, we're just playing a numbers game. We haven't really come up with an efficient way to generate interesting inputs yet. So what's being searched for? Well, typically you're looking for like, okay, there's a crash or there's no crash. I expected this input, like, what the output should have been, and you got something different. So that's interesting. I gave the example of tainted or untainted input before, but something like cross-site scripting attacks, I see a pop-up come back and now I know, it got executed, right? And if the program, if the fuzzer is built to look for crashes, you could always wrap a wrapper. You could create a program that kind of calls the other program and translates that behavior to a crash, right? So if you have a way to kind of build on top of things, which you should always be able to do, you can repurpose any of the common off-the-shelf fuzzers to look for a particular case. So we'll use that trick later. So I want to, before we move on to the kind of gray box testing, I want to make an observation here. So there's this nice tweet. In fact, it's 2 tweets, both there because you can't fit all those in one tweet. And I even quoted this in my PhD, which is fun to figure out how to quote Twitter. But, you know, this illusion that your program is manipulating the data is kind of wrong, actually, right? It's the data that's driving the program. So the program, you've laid out all these kind of control flow paths, you know, if this, then do that, right? And some people like to think about it as like, I am taking a program and somehow transforming that data into the output, right? But it's actually the other way around, that the data is really driving the program, right? So that we have to think about the data and the control flow in the program. So keep that kind of observation in mind, and let's think about what we could do with a little more information, right? So gray box, I'm allowed to kind of look inside the program now. Here I gave the whole program, but imagine I'm only allowed to look at some of those things. Well, let's draw that program as a flowchart because I like to visualize it that way. And let's think about all of the places where data could change the behavior of the program. That's all those branch points, right? And if we were allowed to look at something at runtime, right? If I were to add like these monitors on all of those branches and see, you know, which path the program was taking when I fed it a particular input, I could gain some insight into how that program is behaving with respect to the input that I fed it, right? And if we can correlate that information, we could use that to generate new inputs that drive us deeper into the program. So this is kind of the key observation that guided fuzzing takes. And basically the idea is to have this kind of feedback loop where we will instrument the program, we kind of put those like little monitors at the branch points. And when we feed it an input, we see what happened and we learn something. So we know, oh, this new input, when I fiddled this one bit, took me in a new direction. And I've never seen that direction in the program before. So what I could do is kind of, you know, keep that one bit fixed and maybe fiddle some different bits and see how that behaves, right? And you can start to get this insight into how the data is driving the program. And that's really kind of the bare bones explanation of how this AFL fuzzer works, right? And this is the kind of industry standard. You can see this fuzzer presented basically everywhere at conferences. I've seen so many talks on AFL, but that's how it's working underneath, right? And that concept is pretty interesting because I'm going to show you some other techniques later that are like a smarter tool. They're going to somehow compute the correct input that takes you down the path that you're interested in. But AFL is really just playing this game of economics. They're trying to say, what if I could just guess very efficiently what the input is that does the thing that you're interested in, right? And the way it does that is by very, very lightweight instrumentation. Basically, you can create an array that has a bit at each of those branch points. And if you flip one of those bits, you know you took either a true or false branch, and you can translate that very quickly back into a guess about how you should mutate the input to take you down a different path. And the whole heuristic is, I just want to see as much of this, you know, if we think of this as a graph, I want to see as many of those paths as I can. And we're going to differentiate each of the paths. And this has a huge trophy case of bugs. So like back in 2018, I had 371 plus bugs in, you know, pretty big name programs, things like DNS, things that, you know, one of the bugs that was supposedly could take down the internet, right, was found by AFL. So, so this is a pretty efficient heuristic, actually. And that's really all it is. It's just a collection of hacks and heuristics that have turned out to be pretty effective. So, you know, remember I kind of said that insight, that data is driving the program. And once you start to learn things about the program, you know, we realize that the program's imposing some constraints on what that data has to be. So I find this totally fascinating. So this is AFL. And these are just from AFL's blog. I didn't do this study myself, but basically they took libjpeg, they hooked up AFL, they didn't give it any information really. They gave it a test input string of the word hello, which is obviously not a JPEG file. And they said, just keep fuzzing JPEG. Right. And eventually you're going to start to learn things, right? So the things you might learn are like, oh, well, all JPEG files have to start with this magic byte sequence, FFD9. So I can't fiddle any of those bits because those are fixed bits, meaning I have to have that set or else it won't parse the JPEG file. I won't get deeper into the code, right? So as you get deeper into the code, you start to learn things. You start to figure out what bits are fixed. and you can start to generate things. So the picture on the top are just randomly generated JPEG files that actually parse. And these were just generated by looking at how the inputs, randomly flipping bits were affecting the program. And then at the bottom was for the same experiment, but for a PNG file, which was after you've generated a bunch of files that got you to a certain point in the program, we could ask, what are the properties, right? We could start to see that it started to identify metadata. It's like, oh, you have to have this like kind of special header that, indicates it's a PNG file, stuff like that. And so I'm going to come back to this idea again later, but the inputs that survive, the ones that drive you deeper into the program, all are going to share some common properties. All right, so I talked about this a little bit earlier, but with AFL, you have to write a Fuzzer Harness because AFL basically makes the assumption it doesn't know how to feed input to your program. Your program will do things like read things from the network, read things from user files, input, keyboard events, all that sort of stuff, right? It doesn't necessarily mean that your program is going to read from just a binary text file or just a binary file in general, right? So you have to write some kind of wrapper around the program that you're going to fuzz that accepts a binary file, which is what AFL is going to produce. That's all it thinks the inputs are. It's just a binary file, right? So you have to translate that binary file to how you're actually going to feed data into the program. So if you're going to fuzz DNS, a network protocol, AFL is not going to generate network calls to DNS. You're going to have to write some wrapper, a function that calls the particular functions in DNS that you're interested in, translates the binary file, and like populates those data structures, right? And so this would be kind of a pain. This is the thing that typically turns people off from AFL because it's not just this like point and go sort of solution. But let's table that. I'll come back to that. I have some ideas on that. And let's ask the question, can we do better than AFL? If AFL is like the industry grade, the industry standard, what is the like state of the art, the bleeding edge, right? Oops, I'm going on direction. And so again, I think to do this, you need more information about the program. So restricting yourself to only be allowed to see the branches is withholding some information from a potential solution. So let's remove all restrictions. Or allowed to look at everything inside of the program at this point. And I want to look at a different approach. This is symbolic execution, which I said is somewhere between static and dynamic analysis. So symbolic execution basically starts with kind of what we were looking at before and maps out all of those control flow paths, all of the, the branches. And it also maps out all the relationships between the data. So like, on the right side here, we see Y is assigned the value of this read function call, right? And then Z is the product of Y times 2. Then we have this branch. So like if Z is 12, then we're going to fail, otherwise we print OK. So if I were to say, I'm not allowed to just feed inputs randomly. I have to be smarter. Well, we could do something like symbolic execution. We could say, I'm interested in when the program fails. So like, how do I get the program to take this path that goes through the true path of this branch, right? So it's going to kind of start reasoning backwards. And we can do this fully automatically. So we can say, oh, in order to do that, you have to say, well, Z has to be equal to 12. And Z is Y times 2. So that means Y must have to be 6, right? So we're not giving actual concrete values to our variables. What we're doing is we're treating them as symbols, right? So we can actually get mathy, we can write a bunch of algebra equations, and then we can solve for them, right? And the cost of those solvers, we kind of like sweep that under the rug. We say, well, SAT solvers, SMT solvers, which are building on top of SAT solvers, which just solve Boolean equations. SMT solvers add integers, reals, string theories, things like that. We'll mix those in. We'll say, as long as there's a good improvement in mathematics that we can get better SMT solvers, which they are getting a little better, but it's not getting better at the rate that I think industry and academia are claiming they're getting better. The time it takes to compute this correct path versus the time it takes AFL to just kind of smartly guess the right path really kind of depends on the problem. But most of the time, AFL has been winning that game. So, but it's still a cool technique. I'm not discounting it. I think that we should continue research in this direction. And in fact, you can make these problems really hard for an SMT solver. In fact, if I wanted to do an NP hard problem and force it to do prime factorization, I just change this condition. I'll say if A times B equals C, and then I'll set C to be the product of two large primes. And now all of a sudden, if it treats A and B as symbols, it has to do prime factorization of C to figure out the values of A and B, right? So this can be really hard, and that it's an economics game, right? There is some cool plugins for this. So there's if you have a IDA license, which I don't, there's a cool plugin called Ponce that you can, here they're just solving a little crack me, capture the flag challenge, which I think actually was from a CTF. They have a flag and it's supposed to, print the flag. So, I want it to get to this pass. So compute the inputs that I would have to enter to this program to print win, and that's the flag, right? So we can do this. We're not running the program. We're just generating the solution by computing it directly. All right, but what's the problem with this? Well, remember that path explosion problem. Every path you want to consider, well, that's a lot. We also have potentially very expensive problems that we're solving the solutions for. So in practice, these don't tend to scale very well to very large systems. So what we can do is we can kind of mix things. We can say, well, I'll do symbolic analysis for the things that I can do. And if the state space gets just too big, what I'll do is I'll just concretize some of those variables, and then I'll execute it and run it until I get past the point where I can't track all the state space in memory, right? Because in symbolic analysis, every time we hit a branch, we have to fork that symbolic logic, right, and track all these different states. And there's a lot of tools to do this. So Anger, some of the CLE and Dart were a little older. Microsoft has one that's an internal tool only, but these are cool. But then you realize they're running on giant server farms. Anger actually can run locally. But a lot of these will require quite a lot of cores because you're either fuzzing a lot or you're doing a lot of symbolic logic, which is just very expensive. Okay, what's the state of the art? And some of the best literature we can find on this is, comes out of DEF CON actually. So DARPA's Cyber Grand Challenge was a capture the flag competition where we would put out vulnerable programs, and there were no human players. All the players are, these computers out here in the background, right? And we, sorry, I say we, but I was there just in the audience watching and having fun drinking a beer. But there were no human players. The machines were supposed to 100% automatically solve the challenges, right? And the idea is to detect the program vulnerability, patch the program if you can, because other people are going to be developing exploits, which they'll fire against you. And you're allowed to, automatically reverse engineer an exploit and turn around and fire it at someone else. And there's no human players, right? So this is pretty interesting, televised, but start looking at the research that comes out a year later, because, all the teams are going to publish the papers, and that's when it's interesting to dig into this. So I kind of want to read between the lines. So all teams kind of published essentially the same combination of strategy. And I know there's a few teams that will object to this, but almost every team was running AFL, which I think says something big, right? They're using that guided fuzzing strategy mixed in with their secret sauce. And if you look at the breakdown of the vulnerabilities that were found, many of them were just found with AFL. A few were found with different techniques. So some techniques will, like symbolic analysis, that symbolic execution, will do better in a situation where AFL might not be able to efficiently guess it, right? So there's kind of a blend. Some techniques will do better on certain types of instances of bugs. And I won't say like a particular class of bugs because there's a lot of kind of factors that go into that. And so everyone kind of had their secret sauce, but it was kind of a lot of fuzzing stuff underneath. And if we look at, okay, well, how are they actually fixing the vulnerabilities? Well, they were more like generic patches, things like adding stack guards for fixing a class of vulnerabilities. And a lot of times we would see that teams would fix a class of vulnerability, but couldn't actually produce an exploit. So they didn't actually know the input that would cause the vulnerability, but they knew how to fix the type of vulnerability, which is interesting because all of the vulnerabilities were known ahead of time. So it's interesting. Another thing that I noticed was that the difference between, the first score and the last score was actually pretty close, right? So people were neck and neck. So there wasn't like one approach that really came out and like really rose above the rest. So I want to ask the question, right? If we're just kind of using symbolic concolic execution, this white box testing mixed with something like a fuzzer, can we do better? And again, I think we have to involve more information. And if we're already allowed to look at everything in the program, well, what else is there to look at? And I think that can come from this observation that if we take a human, any of the people in SecDSM that have gone to a CTF, that, a human armed with even a simple tool like Notepad with Control F find, right? Something like that, running strings over a binary, those people are still finding bugs that huge racks of these supercomputers can't find. In last SecDSM presentation I gave, I talked about this CVE 2002-1-3-7, which is pretty interesting. It's about 50 lines of code. It's a buffer overflow, and it represents the current, basically only a few approaches and tools can even barely handle that, but it's the toy example of the real one, which has 3 nested while loops, has go-to pointer, all the things that program analysis just trips over, right? And a human found that first one, assisted with some tools, but machines still can't find that one, even though we know exactly what it is. So let's remember that all the programs that we really care about at the end of the day are created by humans. They're created by humans with the assistance of a tool. So we shouldn't really have this asymmetry. We should allow humans to help with the analysis of the tool, right? And humans, when we write code, we naturally imbue that code with additional structure. Because if we're thinking about that one function in the Linux kernel that I told you had more paths than there are atoms in the known universe, well, a human doesn't think about the complexity of software that same way, right? We don't think about, I can't even fathom how many paths that are. Really what they had were, one check that was asserting that true is true, basically, and they would check these sort of things for each wire in the circuit. And it was just kind of a sanity check, right? So you find the pattern after the first 2 branches, and you're like, oh, it's just this repeated 265 times or whatever it was. And that pattern, those things like design patterns that we bake into code, give us more structure. So when we force machines to solve these really hard problems, like enumerating all the paths in the program, solving all these different conditions, we're forcing machines to do things that, well, yes, machines are good at doing a lot of things very fast. They're not good at doing that many things that fast. But if we were to teach the machine, give it some of those insights, right? Like, oh, it's just this pattern repeated this many times, where humans are very good at pattern recognition, then we might be able to make it so that machines don't have to solve the hard problems. They can reason about it in a different way that lets them avoid that problem. So this is the premise of DARPA's chess program, which my employer does work on. I participated on a similar case study at Iowa State, right? So we were looking at matching the lock and unlock pairing in the Linux kernel. So if you have a lock and you forget to unlock it on some later path, you have a deadlock, or you have a denial of service attack. But in order to do that, it actually involves an expensive analysis trying to figure out what the data are, figuring out what pointers are in C, basically. And that is a very expensive problem. We can tell a machine to do it, but it's going to take a long time. So the current state-of-the-art tool was basically trying to solve this and would time out on a huge number of instances in the Linux kernel. But then we noticed, oh, there's actually some structure. The Linux developers are not stupid people. They follow design patterns. And they would create a unique type just for the instance of lock. And it was never used anywhere else. So if you teach a machine, every time you find this lock-unlock pattern, don't try to solve the pointer analysis problem. Look for the unique type that's used, and the other place where that unique type is used, that's where the pointer analysis problem is resolved. Those are the same thing. They point to the same thing. And if you just apply that pattern, in fact, you can even check it pretty easily to see if it holds true automatically. But if you apply that pattern, suddenly we can solve many of these problems extremely cheaply. And we found several lock-unlock patterns in the Linux kernel, which were later fixed. So I show this slide every now and then, but I want to reiterate that I think that security software analysis is a process. It's not a product. There's no magic bullet. You're not going to find one software tool that is just going to do the thing you're going to do. You can't just take AFL off the shelf, and it's not going to just find the vulnerability. You have to be involved in that process, right? So John Boyd's OODA loop, I think, is a good analogy for this. So the OODA loop is observe, orient, decide, and act. And the whole idea is you're kind of going through this process. So you can imagine a dogfight where two fighter pilots are kind of duking it out. And they're both going through this process, like observe the other pilot, orient, figure out, what that means, where he's at with respect to you, decide what you're going to do, and then actually do it, and then repeat this process, right? And the whole idea is to do it faster than the other guy, right? So you can essentially get inside inside your opponent's OODA loop, where you can decide and act faster than they have a chance to observe and orient themselves, right? And our opponent is just time. So Fred Brooks, he wrote the Mythical Man Month, Turing Award winner, really insightful guy, had this as his thesis, right? So if you can build tools that amplify human intelligence, that's going to be better than artificial intelligence. These AI, machines, a man and a machine working together will always beat a machine by itself. And I think we're starting to finally realize that. If you look at, oh boy, I'm drawing a blank on his name all of a sudden, but the guy that lost to Deep Blue in IBM, Gary Kasparov, yeah, he is also kind of backing this opponent, right? And he's actually proposed that we should have human-assisted chess, right? So you're allowed to walk in and face off with another chess master using your laptop, right? So there's no, it's not just man versus machine. The ultimate battle is man and machine versus man and machine, right? And that's the kind of battle that we're playing out together. So I think that this was kind of my approach, right? This is what I think that I could do. So I thought we could do statically informed dynamic analysis, where we start doing a static analysis. We find the things that are interesting, and then we're going to somehow transition to an automatic binary analysis. And then we'll learn some information and we'll kind of feed that back into the static analysis. And we're going to go through this process, this loop, right, where I learn more and more about the software until I have the information in my mind that I need to reason about the problem at hand. So I'll go through this kind of fast, but I have a lot more on this if anyone's interested. So I want to revisit that question again. What is monitored in the program? Well, I think that, it's not just paths. We have these kind of design models in mind. We have these program invariants, these properties of the program that we know are going to be true. And sometimes those properties aren't true for every case in the program. It's like, oh, well, this is true unless this thing happens, then you have to do it differently, right? So we actually have these properties which are kind of like partitioned separately. We have to reason about different properties of the program at different times. So there had been some work on mining these program invariants. How do you mine these properties out of programs, right? And we can also do this with dynamic analysis. So basically, when we have a bunch of test inputs that drive our program, we can say, well, what are all the things that hold true about the data in the program, right? This was that same idea that AFL was using earlier. So we have a way to do this, but the things that the invariants that it produces are only things that are true with respect to the inputs that you tested. So the question is, could we tie those invariants to something about the path? And, if we can look at the paths, we can break them up into a class, right? So just as a recap, we can take our code, we can draw it as a flowchart like this, right? And this particular flowchart had 6 different paths. I'll call this a control flow graph. And there had been some work out of my group at Iowa State that said, you know what? If we're interested in a certain particular, event in that program, it might be when I write to a buffer to do a buffer overflow, or in this case, I'm interested in the division because if you divide by 0, that crashes the program, right? So if we're interested in a particular event, could we collapse all of the paths into an equivalence class that says all of these paths correspond to whether or not this event happens or it doesn't happen, right? And now we could just reason over the set of paths that all will have the same common property, right? And if I were to look at the properties that are true on those equivalence paths, right? So in this case, if I were to look at the division by 0, well, there's 6 paths in the program, but only 4 of them will ever result in the division operation. The other ones we don't care about. The other 2 we don't care about. But, with respect to that, there's actually only 2 paths of those 4 that are interesting. There's 4 paths of the 6 that are interesting, right? And if I reason about what are the things that are true on the path that leads to the events I'm interested in, now I can get some pretty insightful properties that I'm going to mine out of the program. Because if I mine across the whole program, it's kind of watered down. So let's ask what's executing the program. And I'm going to combine all these at the end. So I'm going to move on to another topic here. Well, one question, do we have to start fuzzing from the top of the program, from the start? And the answer is no. Right? We could write those test harnesses, but we have to, kind of call into code, populate the parameters and functions, things like that, set the global variables, all sorts of goofy stuff. If we're doing a binary, we have to manipulate the stack, all sorts of fun stuff, right? And I wanted to be able to use AFL to do this. And the project I was working on for DARPA was for Java code. So I was interested in, okay, well, can I change the global variables? Can I, mess with the parameters on methods? Can I change the return values of how other functions will return things into the code that I'm actually interested in fuzzing? And could I look at that statically and then say, I would like to start fuzzing here, go, right? Generate some sort of stub and then let the human kind of refine some of that information. So that was the kind of idea, and I won't go too much into detail, but basically we're able to say, yes, we can generate the data structures in memory that the program will need in order to fuzz the section of the program that you're interested in. You can refine that to say, what sort of inputs you'd like to generate there. And then that acts as kind of an automatic wrapper around your program that lets AFL to say, okay, everything's a file. You figure out how to translate it to what that means, right? So we're able to do this. That was a whole paper, nice chunk of my life devoted to that little problem, right? And then again, I came back to this question of like, okay, well, what's actually executing the program? Do I care? Because I said, a couple of those paths didn't really matter, right? So I started thinking, well, what I could do is I could take the original program and I could generate a new program that has the properties that I'm interested in of the first program. And then I could fuzz that restricted program that's only restricted to the things I really care about. And anything I learned about that restricted program will translate to the original program, right? And this should let me fuzz things a lot faster and not worry about all of the extra stuff that I didn't care about in the program. But this all relies on that first step. The human has to say what they're interested in the program. We can't just do this automatically, right? There's some human involvement here. So the new approach is kind of the human will identify the potentially interesting behaviors in the program. Then the machine automatically generates this kind of fuzzer harness for you that instruments the program so that we can monitor the data on those paths and also restrict the program to just the parts of the program that we're interested in. The fuzzer then starts running, uses this kind of guided feedback, right? And drives us deeper into the program, trying to take us there. And eventually the human learns something, and now we might actually repeat the whole experiment again a couple times as we refine our understanding and learn more and more about the program. So let me just check how I'm doing on time. Okay, so quick motivating example, and then I'll move on to a real one, and I'm done. So is this program bug-free? So again, there's a division operation somewhere. So x divided by d. So if d is 0, there's a bug. Right? So I just want to crash this program, and I have a bunch of these kind of like expensive things and some goofy math. So, I read some input from here. I want to ask questions like what's relevant to verifying this program if I want to say it's bug free, right? Or if it's buggy, what are the inputs? I would like to have an exploit at the end of the day. And what are the constraints on the data? So ideally, I want more than just one input that crashes the program. I want the whole family of exploits that crashes this program. So, all right. So we can kind of use some of the techniques that we've done. So this is how we create the restricted program. So we start with that control flow graph. I know that I'm interested in a particular event. So this division by 0 over here. So this is division by 0. These are all the equivalent paths, right? So all the paths in here map to one path in here and map to a particular path in here. What we can do is we can say, you know what, if we started taking this equivalent path or a path that's equivalent to this representative path, then I know you're not going to result in something that I'm interested in. So if the program execution starts going down a path that I know is not interesting, let's add an abort signal, right? So this will tell the fuzzer, stop doing what you're doing, move on to a new input because you're not going to learn anything interesting, right? And we can do that in a couple places. In fact, we can even do it after this because if I executed this line and it didn't cause a division by 0 error, well, then I know nothing interesting is going to happen, right? So I can also abort on a relevant path. All right, so we can do that. That's pretty nice. We can also skip over whole blocks of code entirely, right? So if we start and we say, okay, well, what are all the variables that are involved? We can do something like the symbolic execution. We can walk backwards and figure out all the statements that are necessary. We can compute this slice of the program, right? It turns out these ones in red could never impact what happens here. So what we can do is we could actually just add like a go-to label pair, and whenever we get to that point, we could just jump right over. We don't have to execute it. If it's expensive, it's not going to count against our execution time. And we're actually going to improve the economics game by letting us guess faster by not running the things that we don't care about. All right. So the last thing, finally, is we know the conditions, right? Those are the conditions that have to be true for us to reach that. And those conditions have impacts on the constraints of the data farther up in the program. So what we can do, since we're looking ahead, we can kind of float some of those restrictions farther up in the program, right? So if there's something, if the data is not quite right early on, we can abort really early. And so I wrote a tool that does this. Basically, you click on the thing that you're interested in or the set of things that you're interested in. It collapses, creates all those equivalent paths. Then you say where you want to start fuzzing it from, and it says, okay, cool, here's a harness for you. Generates automatically this program for you, right? So this is kind of the modified version, kind of representative of it. That's this restricted program. And now let's fuzz that. So as an experiment, I fuzzed the original program and the modified program for 15 minutes each. Make it a fair game, right? So the fuzzing speed was much faster on the modified program, right? I can get through many more executions per second. And within that 15-minute period, I found a crash on both, but the modified one, we actually found 2 crashes, which is nice. More crashes is better because now we have a proof it's vulnerable. And let's now look at what are the invariants that held true on that path that led to the division operation, right? So it crashed. It led to this division operation. Let's now see what is the data that holds true. We can do that for both versions of the program. So these are those, I started calling these homomorphic program invariants, but that's just a fancy name for basically the things the assertions that you can make about the data that must have been true for this path to be executed, right? And this is the modified program. We can see we actually learn a lot more, and it's not just because we got more executions. It's because we restricted out the paths that didn't matter, which were actually watering down our assertions from before, right? So, and in order to do that, we're doing a second dynamic analysis that's monitoring all of the execution traces, all of the data, trying to make assertions, see if they hold true, right? And on the original program, that took an hour, and we didn't learn anything very interesting. But on the modified program, that only took a second, actually under a second. And not only did we learn that it's vulnerable, but we learned the exact inputs that crash this program, right? So there's 2 inputs to crash. If you make X1 and Y2, and if you make X3 and Y4, both of those will crash the program. So real quick, before I totally run out of time here, is I wanted to apply this towards the DARPA program that we're looking at. So we were on a DARPA program at the time when I was at Iowa State called STAC, which was Space-Time Analysis for Cybersecurity. And basically, we're looking for 2 things. We look for information leakage in a program or denial of service attacks, these algorithmic complexity attacks. So this was actually a vulnerability that I found in Word while I was helping write the proposal. I pasted in, this billion laughs XML bomb, which basically causes a fork bomb on the string lol that tries to expand this out to a couple gigabytes in memory, and then Word just crashes. And you could try this. I tested it recently. They must have fixed it within the last year, but this worked for several years. Right? So we're looking for things like that. And I wanted to apply this kind of approach that I just pitched. So this application was not supposed to be vulnerable, but we didn't know that, right? We're just told to go find the vulnerabilities. So we did, and we found one. The app's kind of this kind of goofy game. It's kind of like a peer-to-peer game that you play with friends where you're like twisting these lines, kind of a guessing game, right? And we had some kind of heuristics for things that we're interested in. For denial of service, we're looking for loops that we could maybe potentially make forever or run for a really long time or allocate lots of resources. And we have to be able to do this with some input budget, right? So the input budget they gave us was 2 kilobytes. I can't send any file, any input longer than 2 kilobytes. And I have to, have some high success, and there's some other requirements too. But this application, the red teams would try to make it hard. So they'd add goofy code like this that would try to harden it against fuzzers. So this loop will always eventually succeed, but we'll kind of randomly restart the loop a few times. So that makes things tough. It makes symbolic execution harder, just kind of a pain in general, right? So we had some heuristics. We're looking for loops that potentially could go forever. And eventually, we find this little loop here. This was all done on binary. We didn't have the source code, so it's a mix of decompilers and reasoning, right? So we find this loop that is basically the attacker or legitimate user ideally enters some string. It's going to do some operations on the string and then send it back to you. And we find this like, is the string normalized? If not, reduce it until it's reduced, right? So if you can find the string that whatever reduced means, like, is it reducible? If it's not reducible, this loop will run forever and will cause a denial of service, right? So this was really appealing. So we go look into, like, let's go dig into the, this is the call graph. So the, what methods are calling which methods, and some of these are recursive. So it looks like a juicy target. We're pretty excited. We started digging into this. We have this hypothesis, right? The humans involved were generating the hypothesis. So, is there a string that could cause this to go forever, right? So, I want to start, digging into this. There's lots of loops. There's lots of string manipulation, all sorts of goofy stuff going on. This is the control flow graph. It gets kind of messy. Nested loops, all sorts of fun stuff. But, the thing that we're really interested in is just like, I want to keep going back to the loop header. I want it to go forever. So if you exit the loop, that's the path I don't care about. So say I'm not interested in that. Now let's go fuzz this and learn what's, what has to be true about the data if this path can't be taken, right? So hook this up with our fuzzer. We run the fuzzer for 20 minutes, and lo and behold, we get this goofy Unicode output string, right? Because the fuzzer generated it. And this string happens to cause the path, this is reduced to always be false. So the loop goes forever. So great. The approach worked, pretty happy, but I don't understand what this means. So this is the part where you should go back and refine your experiment, right? So, all right. So we know it kind of works. Let's go back and instead of using AFL this time, we'll use the test harness, and we're going to generate strings systematically in a way. We'll start from the small strings, and we'll generate strings that meet certain properties that we learned about from the first execution. So we're going to kind of feed that forward a little bit. And let's find a string that also causes it to crash, with these properties. And this time we're generating data that's much closer to, the data that's going to take us down that path. And within a couple, I forgot how long, but it was very fast. It just starts spitting out strings that crash this. And they're all 3 characters long. Turns out there was a constraint we didn't know about that the string had to be 3 characters long, and that's not a trivial thing. But it had to be 3 characters long, and all the strings were always Unicode. It always had some goofy Unicode character. And it turns out when we start looking for the what are those invariants that had to be true? Well, it turns out that you can make a string not reducible if you can find a character whose uppercase is its lowercase, and the string has to be 3 characters. So it turns out that there's actually 395 Unicode characters that have this property. I was happy to find all of those. And now you can feed any string that's 3 characters long that has one of these 395 characters in it, and you will crash the application. We had a 2 kilobyte budget, but we only needed 3, I guess Unicode. It was UTF-8, so 2 bytes. So yeah, we didn't need much at all, right? So 6 bytes, I think. And not only that, now that we have this deeper understanding about, what are the actual invariants that cause this, now we've identified the whole family of exploits, which is pretty cool. So that's where I'm going to end it. I'm sure I'm starting to run kind of over time here, but I'll take questions, or we can take them offline. Happy to chat about this. Slides are up on my site there. Lots of references, stuff like that. But thank you guys very much for letting me talk with you.
Thank you, Ben. I don't see any questions out in the Q&A right now, so I'll let you go. And if people have questions for him, let them know. Maybe on a Slack channel, or go out to the benholland.com site. And so we're going to take another break. Ben, you can go ahead and stop sharing.
Okay.